Welcome to Finite Element Methods. Today we'll be covering applications of higher order approximations as it turns out to be applied to heat transfer problems. We can solve finite elements, we can solve governing equations using finite elements for a variety of problems. Here, heat transfer is one potential application. Instead of deflections, you're calculating temperatures. Instead of stress and strain, you're calculating heat flux. Instead of deflections, you're calculating, instead of fixing deflections, you're fixing temperature. And instead of applying tractions and loads, you're applying heat fluxes. Instead of body forces, you're applying heat generation. And then instead of Young modulus, you can apply thermal conductivity. But there's some analogy in these ideas, and they're worth discussing. You also have this idea of heat conduction and convection. I discussed this already, but in essence, you can have a very hot component, and you'll be seeing that in the very next project. A very exciting couple thermal problem where the electricity being conducted through the wire is then transferred. The heat is getting transferred to the heat sink, and the heat sink is losing heat through convection because you have a fan blowing. So when you have a hot surface and a hot structure, and you embed the hot structure in a flow that's a different temperature, you're gonna have a heat transfer, and that's given by this difference of T at the wall minus T of the medium, and that gets multiplied by the convective heat transfer coefficient, which is a measurement that one could make. And it's hard to make, by the way. I already covered all this. Remember how the equations of equilibrium for heat transfer problem are given by this. And to recall, K is the conductivity of the material, A is the cross-sectional area, T is the temperature, H is the heat transfer coefficient that tells you how effective you're able to lose or gain heat through by through the medium. So you're basically soaking that structure into a cold or hot air, say for example, or hot or cold water, for example. That H tells you how effective you are transferring heat from the medium to the wall. And so that's why you see this T minus T film. T film here is the temperature of the surrounding. Here I use T infinity. That's another approach that people use to describe the problem. P is a perimeter in this case, but it could change depending upon the problem. But here you can see very easily, intuitively makes sense that the higher the K it is, the easier it is to conduct heat through the material. The higher H is, the easier it is to transfer or lose, to either gain or lose heat by exposing the wall to the medium of interest. So here you have the energy balance consideration. That's a full equation now. We're now including the term for Q. Q is internal heat generation. Um, so you have a component like a wire. You could have heat internally generated from electricity going through, and you'll see that coming up in the project. But there you go. That's your differential equation, and the question is how I go about that. Very easy. Multiply the whole thing by V, right? I have my step number one. I have the ODE of the problem. Multiply the whole thing by V, the weight function. And this is the strong form of the problem. Then I'm going to integrate by part once. And the reason I want to integrate by part once is because I want to use a weak form of the problem. The weak form Galerkin is a much better way of approximating solutions to governing equations, because I can then only have to satisfy the essential boundary conditions through the approximation function, and the order differentiation also has been reduced. So, boom, I'm going to take this V, put it on the left. I put this on the right, and then I integrate by part once the way you see. Remove the prime, draw an arrow, and then draw an arrow like that. The one on the bottom goes back into the integral. The ones that cross goes outside of the integral, and that's your boundary term. V times K times A times T prime. You can see that there, beautifully done. So the weak form of the problem is given here. You can see that there. And notice how Q is K A T prime. So KAT prime is Q. So the heat flux at that point, and then QJ is this much. The heat flux at node J. Remember, I'm deriving these equations for an element. I'm showing you how to derive the element formulation. Because the idea is you solve the problem over an element and then you assemble all the elements together, like I did for the elastic bar in the previous lecture. So once I have that, now I can plug in what Qi and Qj is by effectively satisfying the natural boundary conditions automatically by doing that. Because remember, anything specified on temperature, which is effectively specified on V, is an essential boundary condition. And Ka and T prime, that multiplication is a natural boundary condition. So then I'll select the quadratic approximation again. My temperature approximation looks like this. T is this, like that. I can write it in a vector format, very convenient. The Ti, Tj, and Tk are the nodal unknowns for my element. My element goes from I to J, the whole thing. But the unknowns are really Ti, Tk, and Tj. And I'm going to put that in column vector, the shape functions, and in the column vector row, and the column vector I'm putting the temperatures are unknown. I'll then plug this in. Now I notice here that there's a T prime, so I have to take care of that. And so I have to take this derivative. So I take that derivative. This right here is B bold. I'll call it B bold. This column vector is T bold. Plug that in here for T. Plug B bold transpose. Sorry, I'm sorry. For T, plug in B bold, T bold, which is what you see here. And for V, remember, for V, I'm going to plug in N bold transpose. But there's a derivative, and the derivative of N is N prime, which is B bold. So I'll put B bold transpose instead. Same idea. And notice how for V, I put N bold transpose. You can see that there. PH times, and then for T, I have N bold, T bold, which is this approximation right here, the one I came up with. That goes here. And T infinity goes here. And AQ times V, and V is N bold transpose. And then this can be put in a column vector very simply. This term is called the, you can rearrange the whole thing. So notice how this T bold and this T bold can come outside of the integral. So I brought it outside of the integral. This term and this term went to the right-hand side because there's no T bold in them. So now I have the conductivity and convection stiffness matrix. Kind of stiff, it's not a stiffness matrix, but it is a stiffness matrix for heat transfer problems. So now I have the conduction convection here to the left, the matrix times Ti, Tk, Tj, which are the unknowns at the nodes. Everything else goes on the right. And these are the forcing functions that cause the heating to occur or the cooling to occur. You know all this stuff, by the way. Q, the area is known. T, the temperature of the medium is known. H is known. The perimeter is known. The loads are known at each node. So all this stuff on the right-hand side is known. The conductivity is known. A is known. P is known. H is the heat transfer coefficient is known. B bold are basically what? N bold and B bold are basically what? They are polynomials. So I can integrate that and I'll get numbers. So all these are going to be numbers. And the only thing will be Ti and Tk and Tj left to find. Then once you do that for one element, you have to do it for every single element. And then you assemble the discretized system, impose the boundary conditions on the assembled system, and then solve the system of algebraic equations. And then we post-process the results. Very exciting stuff. So here's a very quick example. For a linear element, what you're going to get when you do it, and I already did it prior to this lecture, you get this. Very simple. 1 minus 1 minus 1, 1, Ka divided by L, where K is the conductivity of the material. The assembly process will be very simple as well. Here, let's look at how this looks like for a problem like this. So calculate the nodal temperatures of 4 elements while maintaining 200 degrees F at this node. And A equals 1 meter squared. L is 1 meter. K is this much. The heat, this is your basically conductivity. The heat enters at node 2 and out of node 4. So there's a heat going in there, but heat coming out of this node, Q30, Q50. Here, notice how these are linear elements. I'm using linear elements right now. 1, 2, 3, 4 elements. So I apply the equation here that I got for a linear element. So for element 1, 2, and 3, and 4, they look the same because it's the same element size, and K is the same for every element. And the length of each element is the same in this example. So all I have to do is write the code numbers and assemble it like you see here. So I assemble it. And when I assemble it, I get this mega matrix. Notice how in the example I'm providing, I told you that this temperature is 200. So that's 200. And these ones are not known. Notice how that's Q1 because this is specified. I told you that heat is going in at 500. There's no heat going at 0 at that node 3. No, nothing going there, nothing going there. 200 coming out, 0, no heat flux there. So now you have 4 equations for unknowns. Solve for T2, T3, T4, T5. Find that, plug that in, and then you can find the heat flux at Q1 that's required to keep that temperature 200 degrees. Let's look at this quick problem. The wall temperature is 200 degrees C. There's a uniform heating source inside the wall of 400 watts per meter cubed, and no heat flow here is insulated, it's adiabatic. So there's no loss of temperature there. No heat flow there is what I meant. So I'll use a 4-element solution. So again, no heat flow going out here or here either. So then obviously things should be getting pretty hot if that's the case. 4-element solution again, 1, 2, 3, 4. Same process, very same process. Let's use a linear element again. All elements are identical, so every single element is going to look like this. Makes sense. When you do it, the 400 is going to turn out to be 50. In the distributed loads, it will be 50-50. You can check it when you do it. I'm just showing you the process, what's going on. Yeah, and everything's straightforward here. So then I can assemble the whole thing. Impose T1 to be 200. And when I assemble the heat fluxes due to the distributed heat fluxes, I'll get 50, 100, 100, 150. Okay. And now I can solve for the temperatures. So there should be equal sign here. So I solve for the temperatures, and this is what I get. Which makes sense because T1 is fixed at 200. Let's apply convection here at the very end. On this end, I'm going to apply convection. I'm going to apply convection on the left-hand side as well. And so there's a little trick here. So I'm going to assemble the elements just like I normally did. But now in the boundary, I have a heat flux. And I call this a mixed boundary condition. If you look at chapter 1 of my book, this is called a mixed boundary condition. This boundary condition is a heat flux. Remember, I can lose heat from here, according to the problem statement, to the medium. And the formula for heat flux is H1 times A times T1 of the temperature of the medium minus T1 at the node. So very clearly that works out. I have to put Q as those values because in this case, that is what is going on at those nodes. I'm losing heat to the medium at these nodes. And that's why this is correct. Now, the complication here is that you have T1 on the left-hand side and T1 on the right-hand side. You have not seen this before. It's the first time we see that. At node 2, you see 0 because I have no heat going in or out. So you have to kind of rearrange the equations in such a way to bring T1 to the other side and T3 to the other side. And when you do that, it looks like this. And now I know H1, A, and T1 of the medium. I know H3 and A and T3 of the medium. So I know K, I know A, I know the conductivity, I know all this stuff. So all I have to do now is invert this matrix to solve for T1, T2, and T3. Great. Let's look at the in convection. So the finite element equation with convection along the rod. So now I'm going to have convection along the whole rod, which means that I have this convection going in here inside the integral because now the convection is through the whole rod surface. And so that's what it is showing up. And it didn't show up in the previous two examples because in those I didn't have convection at the through the whole rod, just on the ends. But here I do, and so I have to consider this term, which I already derived for you. We already did this, by the way. This equation here was derived from first principles, and we arrived at this weak form. I'm just repeating that equation here to remind you. And when you do the integrals for a linear element, you do the integrals, and I encourage you to do that, you get this simple set of equations here. K, A, L, all these are known. And these are your distributor loads, this Q here, distributor load. Q are the point heat fluxes. And when I say load, I mean heat load. The thermal load vector for a uniformly applied load Q, heat load applied Q, is going to look very simple like that. Remember that M bold PHT infinity, that goes to the right-hand side, and that's what that's showing up here on the right-hand side. So a cooling fin is a very interesting problem that's used. You may not know this, but cooling fins are used extensively in a lot of applications so that you can actually cool off the material faster and you're not getting overheating. And that's why if you see the radiator of a car, you're going to see these fins on the surface, is to help you with reducing the heat. So here I give you the boundaries of the problem, the geometry, and the conductivity. The conductivity is given here. The heat transfer coefficient is given here of how efficient you are at losing heat or gaining heat to the environment. The environment is 30 C. I'm going to divide the domain into three pieces, three elements, and I'm going to set the temperature on the left-hand side to be 330. So let's use a three-element approximation. I'll use a linear element. So when I calculate the element conductance matrix, I get this term and I get this term. And for element 1, 2, and 3, and here my goal is to show you how the boundary conditions are applied, less about how to derive the equations because I've shown you how to do that. But regardless, element 1 is this, 2 and 3 is this, and you can see how I get this 38.4 showing up. And the thermal load vector comes out to be this much. I can assemble all three elements together, and when I do, I get these equations. Notice how T4 shows up on the right because I'm losing heat also on this right-hand side. Not just through the body, but also on the right-hand side, that node number 4. We're losing heat to the environment. So we have to consider that. And that's what I did there. You can see that there. We incorporated that term. Now you have to bring T4 to the other side, and when you do, it gets added up to one of the terms here. It's going to be this term that gets modified. And now you can solve for T2, T3, and T4. Let's look at quadratic element, special case number 1. I have a temperature specified here, a temperature specified here, and a middle node here. I have no convection to the outside, no internal heat flow. So this goes to 0. All I have is this temperature applied, this temperature applied. This goes to 0 because I have no convection to the exterior. So that's easy. You can solve for T2 very easily. Let's look at example number 2. I have heat flow going into node 3. So heat flow is going into this point. Now the element node 1 is 100. So now I can solve for T2 and T3 if this is 0 and 200. I'm going to now do a special case where the end node here is exposed to the environment. And the heat transfer coefficient, I called it M. So again, the exterior here is TA, the fluid. So now note how node 3 has T3 here and here, right? here, and here. So I have to rearrange T3 to the other side. When you rearrange and do the whole thing, you can now solve for the middle temperature by bringing T3 to the other side. And that's what the MA shows up here. I think you should do it. You should kind of pause and kind of do it on your own so you can see how this works. It's very exciting. Observations. Well, we have developed an approach to solve ordinary differential equations using finite elements. The approach is actually not very quite systematic. Why? I have to rederive the shape functions for every single element. And the shape function can change from element to element. I showed you that with a few examples in the previous lecture and this lecture. And if the elements are the same, then yes, it's the same, but it's not always the case. And we showed that. Also, the integral varied from element to element. So the approach that we have developed is not systematic enough. And it's not getting us where we need to go. We need to develop a systematic approach to solving finite elements. And again, in industry, I think everyone can agree that you're not going to be deriving these equations by hand. But if you're going to do further research in the arena, then you have to understand this, number one. Number two, some of these things can be very helpful because you can actually have this in your back pocket to check your answers for a single element or two elements, to check your units, to make sure things make sense. It can help you understand what is going on, what is the magic behind finite elements. And that's why we're trying to interweave practical problems using the code, but also tackling the theoretical perspectives. So I hope you learned a lot here. We're going to then move to the next lecture that's going to be using an approach so that we don't have to come up with different shape functions for every element. The integrals can be the same for every element. Wouldn't that be amazing if that was the case? If every shape function was the same, every integrals were the same, the limits of them were the same. And that by itself is a this course is becoming more and more miraculous. Not only I took a governing equation whose solution is quite complicated, and we had Leonardo show us through the advection diffusion problem how the solution for that was very complicated with hyperbolic sine functions. And we demonstrated for you how a simple polynomial approximated the solution to the problem. But now we're taking a step further and saying, I can't solve the whole thing at once. I have to divide the pieces. I have to divide the whole thing into small pieces. Because when I do that, then I'm capable of solving a problem like an aircraft. And that's where we're going towards. We're trying to drive us in that direction. And that's an exciting thing. With that said, thank you so much.